gas evolution reactions were always ones that I didn't like these because you kind of have to memorize them. Now, of course, they make more sense, but there's a special type of reaction that generates a gas. Surprise, surprise. Right in the name. So here, when we mix two aqueous solutions, we get a gas. We get bubbles, it doesn't use the word here. Another word for getting lots of small bubbles is effervescence. So here we've got a reaction. We got aqueous potassium sulfide, aqueous sulfuric acid. Those are reacting to form hydrogen sulfide, which is a gas, and then potassium sulfate. So if we wanted to draw or write a net ionic equation for this, the hydrogen sulfide would stay together because it's a gas, it's not aqueous. Everything else would be aqueous. And so the components of potassium sulfate would be the spectator ions. Another one, so this is a direct formation of a gas. The other ones that we're going to talk about are indirect. So when you mix sodium bicarbonate with acid, so you have baking soda on the desks here a couple weeks ago, 3 weeks ago, whatever it was, you added that to neutralize your acidic solution before you threw it away. That was this gas evolution reaction. So you have the sodium bicarbonate reacting with hydrochloric acid, both aqueous, in this case, aqueous solutions. You form a salt, which is sodium chloride, and you form carbonic acid. That carbonic acid, though, is not stable. And so when it forms, it breaks down into water, liquid water, and carbon dioxide gas. So there's two steps to it. So whenever you mix these things, you're sort of forming, I guess, looking at it from a molecular level, right, forms these bubbles of CO2, not soluble in the solution. The other one that, well, actually, oh, interesting. They don't have them written out this way here. So sulfites and bisulfites. So H2SO3, which my tip to you here is that it's sort of the same structure as H2CO3. H2SO3 also decomposes to form sulfur dioxide gas and liquid water. So here it's all written out as a single step, but you could indicate this as something like 2HCl plus K2SO3. And your intermediates would be 2KCl plus H2SO3. And then that H2SO3 would continue on to become the water and the SO2 gas. So the H2CO3, H2SO3 both have a decomposition step. So there's an extra step to the reaction. Ammonium will break down and make ammonia gas. I guess it doesn't really break down. Right? If you react ammonium chloride with potassium hydroxide, then you get water, ammonia, and KCl, potassium hydroxide. And that one, I believe, happens in a single step. So you just kind of have to memorize these. You have to remember that if you end up with any of these products, H2S, H2CO3, H2SO3, or NH3, that you're going to be getting gases out of those solutions. Yeah. Mm-hmm. And you could simplify it down into like they have written here. Sometimes I do like to write this instead of doing it like that because, right, it's a chemical reaction arrow, so it should still be balanced. But really what's happening here is it's just the H2SO3 that's going on to do that. You could continue to carry over the KCl with it also, there's a few different ways that you could express that this is a separate reaction that's happening. All right, so the molecular equation for the gas evolution reaction that occurs, or write the molecular equation, when you mix aqueous hydrobromic acid and potassium sulfite. So, what's the formula for hydrobromic acid? HBr. We know that it's binary acid because it starts with hydro. So hydrobromic acid, that's going to be aqueous. And then what's the formula for potassium sulfite? K2. SO3. And again, that ITE telling us that it's 3 oxygens instead of 4. Sulfate would be 4 oxygens. And we could do something similar to what we did before with the like precipitation reactions. Because essentially what we have here is a double displacement. So we could write and we have 2 ionic compounds, I should say also. All right, acids are ionic compounds. Sorry, how I did. Swap the cations. And then you drop the anions down. So we're going to get KBr. And we're going to get SO3, 2 minus. We need to balance the charges for each of those. For potassium bromide, we have a 1 plus, 1 minus, so it's just KBr. For the sulfite, we need 2 hydrogens. And so those will be our products. And that's going to be aqueous. And the H2SO3 is also aqueous. And this is where you need to remember that H2SO3 is not stable, just like carbonic acid is not. Sulfurous acid isn't. Give myself more room. I'm going to do this the other way. So we can say, okay, KBr is still going to be around. That's going to be aqueous. But now our H2SO3 is going to break down into H2O, which is a liquid, plus SO2 gas. Yeah. Yeah, now we'll balance it. You can really balance it. Maybe we should have balanced it at the second step. Really, either way. Yeah. Actually, no, it is. I think it is easier to balance. So if we balance this middle one, then the KBr stays the same. We'll just change if there's a coefficient on H2SO3. That'll change the number of H2O and SO2. So yeah, we need. Well, what do I need to balance? Yeah, what coefficient does that need? 2. Anything else? HBr is also a 2. Yeah. And then, yeah, because we made this KBr. Oops. Did I? Oh, yeah, I undid the. And then this. 2 there also. Yeah. There you have it. And yeah, you could really just memorize these. The only kind of thing that could change here is that your acid might be different. So if this had been a binary acid, I'm trying to think of one other than sulfuric acid, but sulfuric acid, right? If sulfuric acid had been in there, we wouldn't need any of these 2s, or we wouldn't need 2s in the same spots, right? So depending on what's in there, it's always going to be SO3. I guess this could be a different cation, right? It could be magnesium sulfate or sulfite. But memorizing these SO3 or H2SO3, H2CO3, NH3, and H2S, those are all the things that are going to eventually form gases or already be gases. Okay. So next kind of reaction that we're going to talk about are oxidation reduction reactions. These are going to necessitate explaining a few other things to go along with them. And these are probably the most involved. Actually, I'm not going to say probably. These are the most involved of all the reaction types. Pretty much all of the other reactions that we've talked about up to this point have been ionic in nature. So we've got things with different charges, and we're rearranging those charges to form new things. In an oxidation reduction reaction, also called a redox reaction, right, just shortening reduction and oxidation together, they involve the reaction of a substance with oxygen. And as we'll talk about in a little bit, they also involve an exchange of electrons. And that's really at the core. But early on, when they were naming reactions, they noticed, well, they called this whole class oxidations because they were reacting with oxygen. And generally, if something's being oxidized, you're adding more oxygen to it, at least in general. So just looking at these few reactions as examples, all right, iron reacting with oxygen, that's oxidation. And also notice that this is elemental iron, no charge. This is elemental oxygen, as it exists in nature, no charge. Different from other reactions that we've done. Same here, burning things. Combustion is an oxidation reduction reaction. So is the, well, this is again another burning reaction with oxygen. Combustion, there you have it. Fun fact, hydrogen-powered cars are essentially, what's the word that I want to say? It's disconnected combustion of hydrogen and oxygen to form water. You're just forcing the redox reaction to take place through a battery or through an engine and use that to power the car. But it's the same reaction that's happening. And so we could also have something like this where we have sodium reacting with chlorine now. Now there's no oxygen involved in this reaction, but there's an electron transfer taking place. So prior to the reaction, we have elemental sodium, elemental chlorine, neither of which have charges by themselves. If you remember some stuff about from Chem 20 about, well, I guess the charges that sodium and chlorine want to form are involved with either gaining or losing electrons. So sodium in this case really does not want to have its one valence shell electron, and it wants to get rid of it. And chlorine really wants to get a valence shell electron from somewhere, so they can both have complete octets. And so through a handshake, they trade that, the sodium trades its electron to chlorine, and now this compound is ionic, right? Added to water, this would be Na plus and Cl minus. And now they'd be charged because they exchanged that electron. So if we take a look at these reactions, sodium reacting with oxygen, sodium reacting with chlorine, both of these reactions involve a metal reacting with a nonmetal, and they both involve reactions or the conversion of our free elements into ions. And depending on the metal and the nonmetal, right, different numbers of electrons being exchanged. Because remember, any ion is has a, I don't want to say this. An ion has the same number of protons, usually the same number of neutrons, but it has a different number of electrons. And so we're only ever changing the numbers of electrons that things have. And because electrons have negative charges, if sodium loses one electron, its charge overall becomes more positive. You can kind of think of this as like a, I don't know. It's almost like therapy for the sodium. It's getting rid of its negativity, right? It's becoming a more positive element. Chlorine just soaking it up. Oxygen's just soaking it up. So for these conversions to happen, we have to gain or lose electrons. Atoms that lose electrons are being oxidized, while atoms that gain electrons are being reduced. There's a bunch of different mnemonics for this, right? So ways to remember it. This is the one that I like, oil rig. Oxidation, let me underline, right? Oxidation is loss, reduction is gain. OILRIG. Does anybody have another one? Does anybody like a different one? Good. Nobody likes the wrong one. Just kidding. If you remember Leo goes grr, or if you have something else that you like to use, that's fine. I will be referring to oil rig. So important too, I guess, to point out, like when we're looking at these sort of representations of these reactions happening, think of this as before and after. So in our before, sodium has that electron, part of the atom, part of its nuclear structure. This is the after. Now the electron is outside of the sodium, right? It's lost it. They've been separated. I think that sometimes when you're first starting to read these, you could look at this side and say, oh, the sodium has the electron. But no. This is it giving up that electron. And similarly with the chlorine, we got 2 chlorine atoms, 2 electrons. So before, doesn't have those electrons. After, they've been incorporated into the element and becomes an ion, chloride. Okay. The transfer of electrons doesn't have to be a complete transfer. So complete transfer is like the metal and the nonmetal forming ionic compounds, right? They become fully ions. Other reactions, though, you'll end up with somewhere in between a shared state of those electrons. So hydrogen and chlorine react to form hydrochloric acid. Well, actually, this is an example of where they're being shared unevenly. Hydrogen bound to a hydrogen, they're shared evenly. Chlorine bound to chlorine, those are being shared evenly. But after this bond, this new bond is formed, it's uneven. So the electron density of chlorine has increased. And since the chlorine's gaining more electron density, it's being reduced. Reduction is gain. And since the hydrogen is losing electron density, right, oxidation is lost, so hydrogen's being oxidized. Okay, so like I said before, in our previous reactions that we've looked at, everything has a charge, or everything forms a consistent charge. So you look at the periodic table and say, oh, magnesium forms a 2+ charge, chlorine forms a 1- charge, they have to combine in this ratio, and everybody's happy. In redox reactions, we have something called an oxidation state. And that's defining sort of the level of oxidation or reduction for any given element in a reaction. And it's a bookkeeping system for these electrons. And it's not, oxidation states are not ion charges. Oxidation states are not ion charges. This is confusing because sometimes the oxidation state is the same as the ion charge, but that's just, I guess, coincidental. One does not define the other necessarily. And more specifically, you can measure an ion's charge. The oxidation state is just again, a bookkeeping system for electrons. So we have to assign oxidation states for any given chemical reaction so that we can determine if those oxidation states change, because it's when the oxidation states change that we have a redox reaction. Any other time it would be some other type of reaction. So the first one is that free elements have an oxidation state of 0. And so that's going to be any element that occurs in its elemental state. Get the periodic table down. Oh, got it to stick on the first try. So really anything that's a metal will exist, except for mercury. Mercury is a liquid. All of the metals will exist as solids. So if we see copper, especially if it's written in a reaction as copper solid, we can assume that that's copper metal. Because if it was part of the solution, it'd be aqueous. And if it's part of the solution, it's going to be an ion. Some of the other ones that are tricky are the Brinkelhoff elements. So anything that exists in nature as a diatomic or a molecular element. So chlorine, for example, would have an oxidation state of 0. Both of those chlorine atoms would have oxidation states of 0. Okay. Monoatomic ions have oxidation states equal to their charge. And this is where I was saying sometimes the oxidation state is the same as the charge. Not always. They're different things, but when you have an ion by itself, like calcium or chloride, the oxidation state of the calcium here is going to be +2. The oxidation state of the chlorine is going to be -1. And so this is one way that we distinguish between oxidation states and charges is the sign goes in front for oxidation states. It goes after for charges. And then for any, well, we want to figure out the oxidation states for individual atoms. So in any neutral compound, all of the oxidation states of the elements in that compound have to add up to 0, which is similar to our ionic compounds. So water, the oxidation states of hydrogen and oxygen will add up and they'll equal 0. So one of them has to be negative and the other one has to be positive. And then for an ion, again, oxidation states are not the same as ion charges, but in an ion, all of the oxidation states will add up to the ion charge. So nitrate here, the oxidation states of nitrogen and the 3 oxygens have to add up to -1. And then in their compounds, ionic compounds, metals will have positive oxidation states equal to their ion charge. Again, oxidation states are not the same as ion charges. Okay. And then for the nonmetals in those ionic compounds, they'll have oxidation states according to the table, actually, not just ionic compounds. Any compounds, they'll have oxidation states according to this table on the right. And this table is hierarchical, which means that the top, or the higher up on the list it is, the more priority it has. So fluorine or fluoride, I guess just fluorine or fluoride, is always going to have an oxidation state of -1. Doesn't matter what it's bound to, always -1. Hydrogen's always going to be a +1, even if it's bound to fluorine, because they're opposite. Oxygen will be -2 unless it's bound to fluorine. So if fluorine and oxygen form a compound, the fluorine has the priority. So if I drew a compound, an insane compound like OF2, we would first take a look at our hierarchical table and say, okay, fluorine's the highest on the list. It has an oxidation state of -1. Then because there's 2 fluorides, the fluorine, those would be like 2 times the -1 oxidation state, plus whatever the oxygen is, has to equal what? What's the overall charge have to be? No, so the overall oxidation state. Dang it, I did it. So the overall oxidation state for the compound has to be 0. Yeah. Well, I said charge, but I meant oxidation state. Yeah. Anyways, okay. So yeah, overall oxidation state has to be 0. So the oxygen has to be what? +2. So this will be +2 plus a -2, and that'll equal 0. So that's how this hierarchy thing works. And then once you get past oxygen, we just throw groups in, right? So these groups are going to exclude things that are higher on the table. So group 7A is this one, fluorine, chlorine, bromine, iodine. Fluorine, though, is always going to take priority even over those. But then everything else, chlorine, bromine, iodine, those will always have oxidation states of -1, unless they're bound up with something higher on the table. 6A is going to be -2, 5A is -3. You can have fractional oxidation states, which is weird, but you can. And then the sign, like I was saying, sign's always written before the number and not after. Okay. I know it's a bunch of rules. So, what is the oxidation state here for chromium? Just 0. So this would be elemental chromium. Right? It doesn't have a charge, so it's chromium by itself. That's the other way that you know that something is an element. It's by itself without a charge. How about B? Chromium 3+. +3. So any ion by itself will have the same oxidation state as its ion charge. All right, now we've got two different elements. And when I ask this question, I want to know the charge, or sorry, I'm going to keep doing that. I want to know the oxidation state for just one of that element. So here, the oxidation state, we want to know the oxidation state for carbon and the oxidation state on 1 chlorine. So what's the rule for compounds? Yeah, should add up to the charge on the compound. And since the charge here is 0, yeah, the oxidation states have to add up to 0. So which element's going to take priority? Chlorine. And what charge is chlorine going to have? Or oxidation state. Yeah, so each of the chlorines is going to be -1. So then carbon has to be able to cancel out all 4 of those. So carbon is +4. So we want to see this as a sort of equation. So altogether has to equal 0. And let me write it like this. We have carbon, and we have chlorine. So we have 1 carbon. That's going to have to be +4, plus 4 chlorines, and those are each -1. So +4, -4, that equals 0. All right. How about strontium bromide? We need strontium, we need bromide. So bromide is, or bromine is in 7A. So everything in 7A is going to have a 1- or -1, unless it's with something that's higher on the list. +2. Actually, double check this. Yeah, so the other way we know that strontium is going to have to be +2 is that in their compounds, metals have positive oxidation states equal to their charge. So strontium forms a 2+ charge. So in a compound, it's also going to be +2 oxidation state. All right, what's the name of this compound? Yeah, this is sulfur trioxide because, as almost everybody fell for my trap card, the SO4 on the exam was sulfur tetraoxide. Yeah, that one was tricky. Yeah, so because there's no charge here, this is sulfur trioxide. And because there's no charge, that means our oxidation states have to add up to 0. Okay, so we got sulfur, we've got oxygen. Now we've got 2 nonmetals. Which nonmetal has the highest priority? Oxygen. So oxygen is going to be determining whatever the oxidation state of sulfur has to be in a compound with it. The oxygen wears the pants. So yeah, oxygen's always a -2. So -2 times 3 oxygens means -6. So sulfur has to be +6. And how about, and what's the name of this last compound? It's nitrate, because it does have a charge. This is not nitrogen trioxide. So this changes the game a little bit. Now, because we have a 1- charge, our oxidation states have to add up to -1. And which element has priority? Oxygen. Oxygen is almost always going to be oxygen. Sorry, I was trying to think if there's a weird, yeah, okay. I'll show you a weird compound where oxygen's not, but it's not even a weird compound. Yeah, so oxygen, still -2. We have 3 of those, so that's -6. The oxidation state of nitrogen is +5, because there's a negative charge. This is math that feels so simple that it's very, very easy to screw up when you try to do it in your head. So, yeah, just be aware. Yeah. How about hydrogen peroxide? So we have hydrogen, we have oxygen. Hydrogen has priority. And what charge does, or what oxidation state does hydrogen like to have? +1. And there's 2 of them, so it's +2. So what is the oxidation state of a single oxygen? -1. So in hydrogen peroxide, the hydrogen has priority and forces the oxygen to have a different oxidation state. Yeah. These are ones that just a lot of practice. They can be pretty quick, especially once you start getting them down, they go pretty fast. I haven't checked specifically, but I'm sure there's an Alex problem. If there's not, maybe we'll add it. Okay. So we need to know how to do that, because we need to do that in order to assign oxidation states in redox reactions and to see that those oxidation states change over the course of that redox reaction. So remember, oxidation is an increase of oxidation state, but it's a loss of electrons. So oxidation is loss of electrons. Reduction is a decrease in oxidation state, but a gain of electrons. So in this reaction between carbon and sulfur, carbon is going from 0 to +4, and it's losing electrons to do that. So that's oxidation. The sulfur is gaining electrons because it becomes more negative, so it's being reduced. Another way that you can think of this is like, I don't know, first grade math, right? Number lines. But I think this can also be helpful in determining if something's going to be oxidized or reduced. So this is what it means when it says an increase in oxidation state. So if the oxidation state is going to the right, we do different colors. Do what they did. They did blue. So if the oxidation state is going to the right, becoming more positive, that's oxidation. Becoming more oxidized, it's increasing the oxidation number. And then if it's going to the left, it's being reduced. So becoming more negative means it's being reduced, or a lower oxidation state. Okay. Let's do it then. Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. How do we even do it? Assign oxidation states. Going to give everything an oxidation state. So what's the first element there? Tin. And is it, well, what's the oxidation state? Zero. And let's do it like this. We'll write oxidation states under. Cool. Oxidation state of tin. Nice and easy. Now we can move on to, what's this compound? Nitric acid. And what's the oxidation state? Actually, I don't think we've done a compound like this yet. We got 3 different things going on here. Sorry, I'm trying to come up with a generic format for the best way to solve one of these. You can kind of split it apart because we know that it's going to be H plus and nitrate, right? So there's that. No, but we can just assign oxidation states in the order that they have to be. Yeah. So, right, which element has the highest priority? Hydrogen. So that's going to be +1. And then what's the next highest priority? Oxygen. So it's -2. Now we do have 3 of those. So we might want to start working out some of this math. Right, so this is going to be a total of -6. It's a total of +1. And we know that the overall compound has to be 0. So what oxidation state does nitrogen have to be? +5. All right, so just work in order of priority, and then the last element has to make up the difference. All right, what would this compound be? Huh? Just tin oxide? Not di, not di. It's not tin 2 oxide, but that's closer. It's on the right track. Tin 4 oxide. Yeah, this is a tricky one. So the oxygen is going to have a 2- charge. There's 2 oxygens. So this is one that I showed you when we were talking about nomenclature stuff that simplifies down, and then if you do the reverse crisscross thing, you got to account for the fact that oxygen doesn't have a 1- charge. All right, so that's helpful though, right? Because if we know that tin here is tin 4, metals in their compounds have oxidation states that match their ion charge. So what's the oxidation state of tin? +4. And oxygen keeps as -2, -2 each. All right, and what's this compound? Nitrogen dioxide. No charge, no charge. Yes, yeah, so nitrogen dioxide. And again, what's the highest priority? Oxygen with -2. So that's going to be a total -4. So the nitrogen has to be +4. And the last compound, I won't make you name that. Actually, what would be the systematic name? Dihydrogen monoxide, #1 killer in the world. And now hydrogen will have the priority. But hydrogen and oxygen, so happy in water, they each get to have their preferred oxidation state. So nice. So cute. Have you seen Kung Pao Enter the Fist? Kung Pao Enter the Fist. It's a hilarious. Somebody took a Chinese kung fu movie and then dubbed over it, and they put like a completely different character in. It's insane. It is. I think so. I don't think I've seen Kung Fu Hustle actually. Oh, there is a super long cow scene.
Yeah, I think I know.
Anyways, yeah, there's a scene where there's like the chosen one is a baby and he's like rolling down a hill. Yeah.
They roll down the
The lady picks him up and she's like, "Oh, so cute," and then she says, "Bye bye," and then keeps rolling him down the hill. Yeah. Your mom showed you that one?
Yeah, that's a really good movie.
It's yeah. Okay. We did it. Oxidation states assigned. So you can see how getting faster at this saves you a lot of time. And also, you know, your professor not antagonizing you and making you name everything, but practice. So what is being oxidized and what is being reduced in this reaction? So the tin, draw an arrow like this, right, goes from 0 to +4. And if the oxidation state is getting more positive, that means that it's losing electrons, and oxidation is loss, so it's being oxidized. And what's being reduced? Yeah. And the way that we know it's being reduced is, and actually, I should point this out, right? We're saying, does anything on the reactant side change when we go over to the product side in terms of its oxidation state? So tin's oxidation state changed. Hydrogen's stayed the same, right? No change there. And then also no change in oxygen, regardless of the compound that it's now a part of. It becomes part of a bunch of different compounds. So now nitrogen is gaining 1 electron. So it goes from +5 to +4, so it's being reduced. And this is already balanced also. I don't think I added the slides in here for balancing them. Okay, any questions about redox identifying things? No? Okay. So oxidation and reduction always have to occur together. So if you've got a redox reaction, there's something being oxidized, there's something being reduced. If you do your oxidation states and you don't see that, then you did your oxidation states wrong. Or I could have possibly made a mistake when writing the test. Possible. So yeah, if an atom loses electrons, another atom has to take them. It has to go somewhere. A lone electron is very, very, very reactive. And this is where things can get a little bit confusing. So the reactant that reduces an element in another reactant is called the reducing agent. So it's forcing something else to be reduced. And the reactant that oxidizes an element in another reactant is called the oxidizing agent. Remember, these always have to go hand in hand. So if something is the reducing agent, it's forcing that thing to be reduced. It itself is being oxidized. And that's where a lot of the confusion comes up from, because it's almost sounds like it's two things at the same time, but they mean opposite things in a sense. So my advice to you is always first identify the thing that is being oxidized, the thing that is being reduced, and then determine the oxidizing agent and reducing agent, because it really just flips after that. But if you can find that first thing, then you don't have to worry about trying to remember which way it goes. So if we actually go back to this problem, so the tin, the whole problem on there, the tin is being oxidized. And that means it's the reducing agent. And more specifically, The reducing agent is that elemental tin in the reactants. The thing being reduced is the nitrogen, and that makes it the oxidizing agent. You would say that the whole compound, yeah. You would say that the whole compound is the oxidizing. So the nitric acid here is the oxidizing agent because it contains the agent doing the oxidization. Oof. Just flip-flops too much. Okay. Yeah, so let's do this even. The tin, just to make it abundantly clear, HNO3, whole thing is oxidizing agent. Okay. So again, figure out what has been oxidized, what's being reduced. The other, and then it's the oxidizing agent, reducing agent. All right, so determine whether or not each reaction is a redox reaction. So let's give you guys some time with these. So you could look at them. Everybody can figure out if they know how to assign oxidation states. All right, so let's. Is that enough time? Does anybody want more time? Feel free to say one more time. Good. How many of these reactions are redox reactions? Some threes? Yay, nay? So first reaction, how do we know the first one is a redox reaction, or is it a redox reaction? Yeah, we can look at the oxidation states to something other than 0. Since this is lithium, this would be elemental lithium by itself, doesn't have a charge. Sorry, I'm doing oxidation states underneath. Yeah, both of these are elemental, don't have charges. They become part of a compound. And so as a part of a compound, now they're going to have oxidation states. Lithium will have an oxidation state according to its, or the same oxidation state that its charge would be. So +1, and chloride would be -1. So do we have changing oxidation states for number 2? We do indeed. And in fact, this one's even easier because we have elemental aluminum here. And so that's going to be oxidation state of 0. And then we have an aluminum ion. And it's 3+, so that tells us in any metal ion by itself, its oxidation state will be the same as its charge. And we can do this for tin, just for kicks. Now, which of these is being reduced and which one's being oxidized? So tin's being oxidized? Yeah, aluminum's being oxidized because it's losing electrons, or you could even say it's losing oxidation state. Feels weird to say that. And then the tin is being reduced. So then what's the reducing agent? Aluminum. Not on this side of the pond. No. No aluminium here. Extra syllables. All right. How about number 3? Is number 3 a redox reaction? Yes, it is a precipitation reaction. Sorry, it's not a redox reaction. It is a precipitation reaction. And we could do the oxidation states for all of these, but one hint, if nitrate here stays nitrate over here, there's no change in oxidation state, for nitrate at least. Lead here, and we can even use the ions now as like a guide to say, oh, this would be 2 plus charged lead and 2 plus charged lead on the other side, so its oxidation state's going to be the same. And lithium and chloride, their oxidation states don't change either. So no change in oxidation states, not a redox reaction. I guess we should say yes, redox, yes, redox, no. How about number 4? Yeah. So really, if anything, if you ever have elements and they go from being their elemental form to being part of a compound, it has to be a redox reaction. Because the oxidation state of carbon is going to be 0, the oxidation state of oxygen is going to be 0, and over here, oxygen's -2 and carbon's +4. So what's being oxidized, what's being reduced? Carbon's being oxidized, oxygen's being reduced. And actually that's what you'll find if you have oxygen reacting with something. The thing that oxygen reacts with is being oxidized. So oxygen is an oxidizing agent. How about that? Okay. We will come back to balancing redox reactions. But we'll do that next week. All right, activity series. So this is all about, activity series is all about predicting whether a redox reaction is going to be spontaneous or not. So every element, I guess you could say even every compound has a tendency to gain or lose electrons. And you can, in a sense, think of these elements and compounds as having some sort of inherent strength for stealing electrons from other things or holding on to their own electrons. And sometimes things just want to give up electrons. I think actually in Chem 2 last semester, I called this elemental fight club. So the stronger element wins and steals the electrons. We'll look at that in a second. So in this reaction, magnesium has a greater tendency to lose electrons than copper does. So really, copper is stronger than magnesium and steals its electrons. So we have a copper solution and a strip of magnesium metal. And if we look at, we got our equation down here. All right, magnesium is going to have an oxidation state of 0. Copper is going to be +2. Then magnesium goes to +2. Copper goes to 0. So the magnesium is being oxidized, and it lost its electrons. Copper is being reduced, and it stole magnesium's electrons. So whoever wins, Element Fight Club, steals the electrons. So copper ion is a stronger reducing agent than the magnesium, or stronger oxidizing agent. And we can tell that something's happening because there's a reaction that takes place, right? You get the magnesium metal starts to turn black, or it looks like it forms black all over it, and the blue color from the solution fades, which is the copper ions being used up. So the reverse reaction doesn't happen because the copper is stronger than the magnesium. So magnesium's not strong enough to beat up the copper and steal its electrons. And the reverse reaction doesn't happen. Copper doesn't lose any electrons to magnesium, and they just sit there staring at each other. And so we can use the activity series of metals, which lists the metals in order of decreasing tendency to lose electrons. And each reaction on this table is a half reaction, so it's only going to show you the metal by itself, and then, actually, yeah, so these are oxidation, it's an oxidation table. So it's the oxidation half reaction. So metal element on the left, ion plus however many electrons it would lose on the right. And we can take these oxidation reactions and write them in the opposite direction, and they become reduction reactions. So this activity series well, let's say this first. We require 2 half reactions to make 1 reaction. Because remember, oxidation and reduction have to happen together. We need both parts. So if we're looking at 2 elements, whether or not they're going to react, really you're taking 1 reaction and you're taking another metal in that reaction, and then you flip one of them, and that would be your full reaction. The reason that this is written as all oxidations and not all reductions is purely historical. Because at some point people decided, well, we're just going to use this one, and we're all going to talk about it from this perspective. It could very easily be the other way. So if we look at our half reactions on this list, any half reaction on the list is spontaneous when paired with the reverse of any half reaction below it on the list. So if we take lithium, for example, and we pair it with any reaction here, flipped going the other direction, lithium wins that fight. So this is essentially the metal redox tier list for Elemental Fight Club. So if we take, actually let's pull out the magnesium. So we got magnesium. So if we pair this, we have magnesium metal. I guess it depends on your perspective here a little bit. And we want to pair that reaction. Now, where's the reaction first? Mg2 plus 2E minus. And we're going to pair that with copper, because that's the reaction we saw earlier that was spontaneous, right? Magnesium metal, copper ions. And that was the reverse reaction here. So we've got copper 2 plus 2 electrons will give us copper metal. I guess the way I explained it earlier, the lower element is stronger. So magnesium plus Cu2 plus going to magnesium 2 plus 2 minus, whoops, not 2E minus, sorry. Cu solid. That was the spontaneous reaction we saw before. We were starting with this half reaction and pairing it with another half reaction reversed below it. If we take this whole thing and we flip it around, now we're taking copper, going to copper 2 plus 2E minus. So the only things that copper metal will react with are going to be silver and gold. Because magnesium metal is higher than it on the list. And so this reverse reaction of Mg2 plus 2E minus give Mg metal. Combining those two would result in a non-spontaneous reaction. Okay. Oh yeah, so the ones at the top are most easily oxidized. So they lose their electrons most easily. The ones at the bottom are the most difficult to oxidize. They're the hardest to steal the electrons from. So which metal is most easily oxidized? That means we need to go and look for where sodium is on the list. Actually, sorry. Out of these 3, sodium, chromium, and gold. And we want ease of oxidation. So we've got sodium, chromium, and gold. Sodium's the easiest to oxidize. So sodium can have its electrons stolen by everybody below it. And actually, this is one of the things that makes things like silver and gold so non-reactive, because they're really, really hard to oxidize. If you have this gold metal, there's very little that it will lose electrons to and react with. So sodium would be easiest. And this would be the second easiest, because it is a spectrum. And this would be the hardest, at least at this list. All right, so which of the redox reactions would be spontaneous? Let me see, I can do If I do this, there you go. So which reaction's spontaneous? Yeah, so for A, we've got zinc. And actually, right, the way to use this is to find in your reactants which one is the metal. And so you find that reaction on the table first. So that's the zinc reaction. And then if nickel's metal reaction is below it on the table, which it is, come on now, that will be spontaneous. So this one's spontaneous. But now is a zinc calcium reaction, is that reaction going to be spontaneous? So we find zinc again, and then we say, is calcium below it on the oxidation list, or oxidation activity series? And it's not. Calcium's higher. So we're always starting with the element that we have that's a metal, and then we're checking from there, do we go up or do we go down on the activity series? If you go down, it's spontaneous. If you go up, it's not spontaneous. This would be non-spontaneous. And actually now you can go back and look at the copper cycle lab, and a lot of the reactions, most of the reactions there are redox reactions. Because at the first reaction, we took that metal. And so this is just the activity series for metals. There's a lot of other compounds that slot in between these. So where would you expect nitric acid, which we use to dissolve the copper, where would that be on the activity series? Yeah. So if something's lower on this oxidation activity series, then it's going to be a spontaneous reaction. So if nitric acid is lower than copper on this list, or nitric acid would be, and so it'll react with the copper metal, cause it to dissolve. Yeah, neat. Any questions about redox stuff? Alrighty.